You're engineering a new drone, and you need to select the right titanium for the chassis struts. You have three options from your suppliers: budget, standard, and premium. Marketing promises the premium material is the strongest, but as an engineer, you need hard data. To find out which is actually best, you pull 10 struts from each bin and put them through a tensile test. You break all 30 items to calculate the average yield strength for each of the three groups. Here is the mathematical notation for framing this test. Our null hypothesis, H0, assumes that the true population means of all three materials are exactly the same. The alternative hypothesis, H1, states that at least one of these means is different from the rest. If you want to justify paying for the premium titanium, your data has to be strong enough to reject that null hypothesis. You must prove the struts don't all come from the exact same population of metal. Your first instinct might be to run 3 separate A/B comparisons, what statisticians call t-tests. You'd compare budget to standard, standard to premium, and budget to premium. But every standard t-test carries a 5% risk of a type 1 error, which is a false positive. When you stack multiple tests on the same dataset, those individual errors compound. Running 3 separate t-tests inflates your overall risk of hitting a false positive to about 14%. That means you have a nearly 1 in 7 chance of declaring the premium material superior based entirely on random statistical noise. You'd be spending your manufacturing budget on expensive parts that offer zero actual structural gain. Stacking localized comparisons is mathematically reckless when you have more than 2 groups. You need a unified method that evaluates everything simultaneously. This is where analysis of variance, or ANOVA, solves the problem. Instead of just looking at raw averages, we need to visualize the shape and spread of the data using box and whisker plots. First, look at the distance between the averages of the 3 groups. This spread is our actionable signal. It represents the variance between the groups. Next, look at the width of the individual boxes themselves. This represents the messy, natural variation inside each supplier's own batch. This is our noise, the variance within the groups. The formula shown here gives us the F statistic. It's exactly that relationship, a mathematical ratio calculated by dividing the variance between the groups by the variance within the groups. Let's test this intuition. Take a look at these 2 scenarios. Pause the video and decide which one of these would yield a higher F ratio. The answer is scenario A. Because the individual boxes are narrow, the internal noise is very low. Combine that with a large distance between the groups, a high signal, and the math outputs a massive F ratio. The F statistic isolates exactly how clearly an actual difference stands out against the backdrop of natural, random variation. Running our data yields an F statistic of 43.14, clearing our 3.10 critical value. We safely reject the null hypothesis. But there's a catch. ANOVA confirms a difference exists somewhere, but doesn't say where. To prove premium beats standard, you must follow up with post-hoc testing. Here is your test engineer cheat sheet. Rule 1. For more than 2 groups, use ANOVA to avoid compounding errors. Rule 2. Signal is variance between groups, noise is variance within. Rule 3. F statistic equals signal divided by noise. Bigger F means stronger proof. When making critical engineering decisions, ANOVA cuts through the messy variance of the real world, giving you an objective mathematical truth.